This video is part number 3 of my Galvanic cell series. And for this part, I'm going to cover the different types of half cells, electrodes, electrolytes, and salt bridges that you might encounter. So just as a summary from a previous video, here's a list of definitions that goes through all the key terms that we're going to cover through today. First, we're going to begin with half cells, which is basically a structure that contains an electrode, which is a piece of solid metal, and an electrolyte, which is the surrounding solution in the beaker, which is colored in yellow here. So let's go through what materials we can choose for the electrode and the electrolyte. And the good thing about this is that you can get all this information from your electrochemical series, which I'll link below. If you take a look at your electrochemical series, the most common type of reaction looks something like this. You have an aqueous metal and a solid metal, as you can see by the states. And for example, we have a reaction involving copper 2 plus aqueous and copper solid. So if I were to make a copper half cell, the electrode would need to be made up of the solid metal. So in this case, it's copper solid. And the surrounding solution must contain the aqueous metal. So in this case, it's copper 2 plus. And the reason we need both of these is because we want the flexibility for this reaction to move in both directions. Now, what happens if we don't have a solid metal? This reaction contains iron 2 plus and iron 3 plus, which are both metals that are in the aqueous state. And what I'm about to say is also true if one is aqueous and the other is liquid. But in both cases, we need to use an inert electrode. Inert just means that the electrode does not react with anything else. And this is because we don't want to have an electrode that is going to cause unwanted side reactions. So basically we want the electrode to do nothing apart from act as a surface for the reaction shown here to occur. And also, it needs to be solid because we can't have an aqueous electrode. So some common examples of inert electrodes are platinum or graphite. And then for our electrolyte, we have both of these aqueous metals in our solution, like so. So both iron 2 plus and iron 3 plus. And then for our final case, let's look at this reaction, which has hydrogen gas. Now, using the same logic as before, we can use an inert electrode because we don't have a solid substance in this reaction. So we can also use platinum or graphite. And you might notice that this electrode is a bit smaller than the other ones, but this isn't something that you have to worry too much about because it's just something unique about hydrogen half cells. So just to make this clearer, I'm going to attach a wire here in blue. You could also do that with the other half cells. But basically, this is the wire that connects the two half cells together. So if you want to merge two of these half cells into a full cell, that's how you would connect them. And then the unique thing about a half cell that has gas is you're going to use a test tube-like structure, and you're going to put that over the electrode. And this allows the gas, so the hydrogen gas in this case, to travel in or out of the solution depending on the reaction. For example, hydrogen gas can travel as indicated by the arrow, and it travels down to the platinum electrode. And that's where it's going to react to form 2 H plus ions and 2 electrons. And the opposite process can also occur depending on what the other half cell is. So these are the main types of half cells that you might see. So now let's take a closer look at the electrolyte. And I've just got the copper half cell here as a reference. Now the first requirement for the electrolyte is that it must be aqueous and ionic. So aqueous means that the substance is soluble in water. And ionic just means we have a positive charge plus a negative charge. So a cation plus an anion. And this is important because we need the ions to move freely around in the solution to conduct electricity, which is the function of the electrolyte. Now, a good rule to help us determine whether a substance will be soluble or not is something called the Snape rule, which basically states that any ionic compounds that contain sodium, nitrate, ammonium, potassium, or ethanoate then the entire ionic compound will be soluble. So let's find some potential electrolytes for this copper half cell that we have here. And just note that all the electrolytes must have the copper 2 plus cation in them, because half cells always contain the aqueous element. So I'm going to show some examples here, and I'll go through whether they're suitable or not. So first we have copper nitrate. So you can pause now if you want to have a think about this. So copper nitrate is soluble because nitrate is one of the Snape compounds. And in that case, it makes the entire ionic compound soluble, regardless of what the other metal is. Okay, what about copper oxide? So copper oxide would not be soluble because it doesn't contain any of the Snape compounds. So therefore, it cannot be used as an electrolyte. Now, with that being said, substances such as copper sulfate are soluble even though none of its compounds are a part of Snape. So it does come down to a bit of experience to remember which compounds are soluble, but the common ones or the common rules usually stick in your head after doing some questions. Now, the word electrolyte is quite a broad term, so there's another place where we can find it apart from the half cells, and that's the salt bridge. And this is because the salt bridge is just a device that's soaked in electrolyte solution. Now, this might be a bit confusing, but just note that the solution in the half cell and the solution in the salt bridge are both called electrolytes. However, they don't have to be the same, and they're usually not the same. So now you might be wondering why I've left requirement number 2 here blank. And that's because when we have 2 electrolytes, one in the half cell and one in the salt bridge, that have the potential to mix together, we need to make sure that when they mix, nothing detrimental happens. And just as a side note, remember that the ions in the salt bridge flow into the half cells. So we need to make sure that when they flow into the half cells, nothing bad happens. And because of this, to make our requirement checklist more generic, we need to consider a second point, and that's electrolytes should not form a precipitate, and a precipitate is basically a solid compound. If something is solid, you can kind of view it like it's locked away from being able to react. So over time, you can end up with less things to react with. And as you can imagine, if you end up with no reactants, there's going to be no electron flow and no electricity being produced. So that's why it's important to not form any precipitate. Now, don't worry if this sounds a bit abstract. Let's go through an example. And to illustrate, I'm going to use a copper-silver galvanic cell. So one of the half cells is a copper half cell containing a copper electrode, and for the electrolyte, we have copper sulfate. And then in the other half cell, we have a silver electrode, and for the electrolyte, we have silver nitrate. And the copper electrode is your anode, and the silver electrode is your cathode. Since silver is above copper in the electrochemical series, but that makes silver the cathode and copper the anode. Now let's explore what solutions we can have in our salt bridge. The first example, let's look at sodium nitrate. And since anions move to the anode and cations move to the cathode, the positive Na plus ions are going to move to the silver electrode, and the negative nitrate ions are going to move to the copper electrode or the anode. And when this migration occurs, let's look at what happens. So when positive sodium ions go to the silver half cell, it can react with the negative nitrate ions. And when you have Na plus and nitrate, that's going to form sodium nitrate. And this isn't too much of an issue because sodium nitrate, using our Snape rule, is soluble in water. So this is not a precipitate. And just note that the sodium ions won't react with the silver cations because 2 positive ions will repel each other. And then on the other side, we have negative nitrate ions moving into the copper half cell. And again, it's not going to react with the negative sulfate ions because two negative charges repel. However, it is going to react with our positive copper 2+. And copper 2+ and nitrate is going to form copper nitrate. But using our Snape rule, we know that anything containing nitrate is soluble. So this is not a precipitate either. And therefore, we can conclude that since no precipitate is formed, sodium nitrate is definitely something we can use in our salt bridge as the electrolyte. Now let's look at a slightly more complicated example. Example 2, we have potassium chloride. Now, for both of these examples, they fulfill the first criteria, which is they're both aqueous and ionic. So we're just focusing on the second point here. And using the same logic, cations to the cathode and anions to the anode, we know that the K+ cations are going to move to the silver half cell, and the negative chlorine ions are going to move to the copper half cell. And again, let's examine the potential reactions. So in the silver half cell, the potassium ions are going to react with the nitrate. And looking at Snape, we actually have both potassium and nitrate. So that is soluble and that is not a precipitate. And then in the copper half cell, we have copper 2+ and chloride ions. Now that is going to form copper chloride. And the tricky thing about this is again one of those exceptions. So copper chloride is actually soluble in water. Now, you might think that's a bit annoying because you have to memorize these exceptions. And that is true to some extent. You should try and memorize some of the solubility rules and exceptions. But in this case, there's actually something else in this question that does not involve this copper half cell at all. So when we have a salt bridge, you don't have chlorine all on one side and potassium all on the other side. It's basically a mixture of chlorine and potassium everywhere in the salt bridge. And it's only when you connect the salt bridge to the entire cell do the ions move in their respective directions. Now, the implication of this is when you first put the salt bridge in solution, there might be some chlorine ions floating around. And the implication of this is that the chloride ions and the silver ions are going to react and form a precipitate. And the precipitate is silver chloride. Now, if there's one exception that you remember, it should be silver chloride, because this is one of the most common types of questions, especially in the Victorian study design. And just for your reference, this was a practice exam question. So it required some extra thinking, but hopefully after you've seen this, it should give you an idea on what types of questions that you might see involving precipitate. Hopefully that made sense. Here's a summary for today's video. And if you want to watch more galvanic cell videos, check out the links below to explore the topics on your screen in more detail.